Okay, good morning. Good afternoon. It's Monday, November 2nd. November has arrived in our class session this week. We're going to explore some more identities this week, some kind of practical identities, double angle formulas, half angle formulas, sum to product and product to sum identities, and do some special use of the inverse functions. So this week is really all about trigonometric identities. And since that is the case, I did this a week ago. Remember, we were concentrating on the exam last week. So we kind of had a week off. So we're going to come back and pick up where we left off. But before we went to the exam, we were expanding our lists of identities. And we had just begun with the sum and difference identities in that week before the exam. So now what we're going to do this week is expand that to the double angle identities, the half angle identities. Look a little bit scarier, but they're not scary. And then on the other side of this paper, these are kind of practical, although they look kind of busy or complicated. The product to sum and the sum to product identities. Now, I won't do these today, so I'm not going to highlight these and get into these today, but we're trying to fill out the rest of this formula sheet right now. I'm reading your exams. Probably sometime by the end of the week, I'll be done reading them and then post them along with your most recent homework. Excuse me, get someone else in the room here. So probably by the end of the week, I'll post your graded exams, updated grade reports, and most recent homework problem. I'll have that posted in your Google Drive folders. Also remember, let me share our website with you. The last week we didn't present any new material. So there is no homework problem, either XYZ homework or written homework problem that you're submitting tomorrow night. You kind of had the weekend off, so to speak. But you can get started on the written homework 8 and the XYZ homework from 5.3, 5.4, and 5.5, because that's what we're talking about this week. So after we get started today, after today's session, you'll be able to do much of that problem and much of this XYZ homework sections. So no homework handing in tomorrow night. You're just preparing for the next homework, November 10. Okay. What else do I want to scan right here? So the outline double angle formulas, half angle formulas, the additional identities, handouts, video we'll post. So nothing extraordinary this week. We're just picking up where we left off before the exam. Okay. The sum and difference identities that we did before we went to the exam last week are really underrated. The sine of A plus B, or the cosine of A plus B, or the tangent of A plus B. Now you can't simply say sine of A plus B is sine A plus sine B. That would be too simple. And in fact, if you just tested out a couple values for A and B, you would recognize that it didn't work. But we rather built this kind of complicated symmetric poem over here on the right side. The sine of A plus B is the sine of A, cosine of B, plus the cosine of A times the sine of B. This mixture of the sines and cosines of A and B, that's how you can calculate the sine of A plus B if necessary. Cosine of A plus B looks similar, but you put the sines and cosines in a different order. You did cosine A, cosine B. You had different sine minus sine A, sine B. And the tangent of A plus B, you could take from dividing these two, but you could also simplify that after you divided. And we gave you that calculation. And write tan A plus tan B, 1 minus tan A, tan B. Oh, go ahead. No problem, Austin. You re-interrupt anytime. No, I'm still reading the exams. I'm hoping I can get them posted back to your Google Drive folders by maybe Thursday. Now, when I finish grading them and post them in your folders, I'll send you an email saying, okay, exam 1 graded and grade reports are posted in your folder. So I'll let you know by email when they're posted there. So I'm still reading them right now. But that's a good question. But the other thing that was interesting about the sum and difference identities is you get kind of 2 for the price of 1. This is the sum identities, sine of A plus B, cosine of A plus B, tangent of A plus B. But if you want the difference of A and B, the difference of A and B, the difference of A and B, the sine of the difference of 2 angles, the cosine of the difference of 2 angles, the tangent of the difference of 2 angles, you just have to change the signs in this formula. So sine of A minus B will be the same structure, sine A cos B, cos A sine B, but it'll have minus sign in there in between. The cosine of A plus B started with a minus sign, but if you want the cosine of A minus B, you put a plus sign between those two. The tangent of A plus B started with a plus and then the denominator had a minus. If you want the tangent of A minus B, then in the numerator you put a minus, in the denominator you put a plus. So some people put the plus minuses in this order to say the sign on top belongs to the sign on top, the sign on the bottom belongs with the sign on the bottom. So when you say A plus minus B and over here you say plus minus, it means if you want the plus, you use the plus. If you want the minus, you use the minus. But if you say plus minus, and then over here minus plus, then it means if you want the sum of 2 angles cosine, then you take the difference of these products. And if you want the difference of 2 angles cosine, then you take the sum of those products. So this is just by way of saying this is what we did before we took a break for the exam. But these 3 formulas give birth to a whole different range of useful identities. So I think I'm going to show you the identities And then I'm going to do problems from the book with these identities. So this is a very calculational thing. It's a very, very practical thing that I can make with the sum and difference identities. And the best way to understand it is for you to see me do problems with it. For example, we can immediately calculate or create the so-called double angle identities. In other words, what if someone wanted you to calculate the sine of 2 times a? Well, just think of 2 times a as a plus a. Let me slide that up, sorry. Just think of 2 times a as a plus a. In other words, if you put a's in both positions, you'd create a formula for the sine of 2a. If you put a in both positions, you'd have sine a cos a plus cos a sine a. Now, the order you multiply doesn't make any difference. So you'd have sine a cos a plus sine a cos a. You'd have 2 times sine of a times the cosine of a. Sometimes it maybe bothers you when you put parentheses around the argument of sine or cosine and when you don't. Usually when people don't have anything inside there but a single letter, they don't bother putting parentheses around it. But when they have more to enclose, then they enclose it with parentheses. But you could do it either way. What happens if I wanted to create the cosine of 2 times a? Again, I can do cos a plus a. I'll replace the b's with a's. And that would give me cos a, which is cosine of a squared, minus, because in the cosine formula, the plus goes to the minus, sine a, which is sine a squared. Now I'm going to leave some space before I go down to the next formula. I'm going to leave some space to fill something in. But I could do the same thing with tangent. What happens if I wrote the tangent of a plus a, replaced each b with an a? Then I'd have tan a plus tan a. That would be 2 times the tangent of a. Divided by 1 minus tan a times tan a. 1 minus tan squared a. So the sum and difference identities allow me to immediately create these so-called double angle identities. And so you say, is there much of a call for doubling the angle? Well, don't think about it this way. Think about it another way instead. If you want to know the sine of 2a and the cosine of 2a, you can get by. It is sufficient to just know the sine of a and the cosine of a. Think about that. If you want to know the sine and cosine of 2a, it's good enough to just know the sine of a and cosine of a and insert it into these formulas. If you want to know the tangent of 2 times a, all you need to do is insert the tangent of a into this formula. I want to add 2 more formulas here because there's another way to write cosine 2a. In fact, there's 2 other ways to write cosine 2a that are useful. Remember, cos squared plus sine squared is 1. Cos squared of any angle plus sine squared of that angle is 1, and I don't have a plus sign here. This is not cosine squared A plus sine squared A. That would just be 1. But think about the famous Pythagorean theorem, cos squared A plus sine squared A equals 1. If I replace this cosine squared with 1 minus sine squared, I'd have 1 minus sine squared A minus sine squared A. I'd have 1 minus 2 sine squared A. Or if I replace the sine squared A with 1 minus cosine squared A, I have cosine squared A minus the quantity 1 minus cosine squared A. That would work out to be 2 times cosine squared of A minus 1. So for the cosine of 2A, you get this triple layer of protection. You get these 3 equivalent formulas. So these 5 formulas, now it is 5 formulas, but it just deals with sine, cosine, tangent. These 5 formulas are called the double angle identities. And later, when we look at the half angle identities, they'll be the same thing, except there's a triple version of tangent, half angle. So let's do an example of using the double angle identities. I'm just going to pick something. Out of the book, let's try 5, 6, 7, and 8. Look at these problems in section 5.3. It's 4 problems, but they all go together very simply. It says, let's suppose that the cosine of x is 1 over root 10. And x is between 270 degrees and 360 degrees. In other words, x is in the 4th quadrant. Now problems 5, 6, 7, 8 say, can you tell me the cosine of 2x? Can you tell me the sine of 2x? Can you tell me the cotangent? Can you tell me the tangent? So let's find all 4. Cosine of 2x, the sine of 2x, the cotangent of 2x, and the tangent of 2x. This is problem 5, 6, 7, and 8. But they all go together. So let me show you how you approach any problem like this. This is partial information about the angle x, right? I'm telling you something about the angle x, but I'm not telling you everything about the angle x. I'm telling you it's in quadrant 4. I'm telling you it has this cosine. But if you know those 2 things, you can find the sine of the angle x. You can find all the other values of the angle x, right? So first step is let's draw the angle x. And I'll see if I can fit this on one piece of paper. Well, see if I can fit this on one camera. Let's keep this over here. And this might be a rough drawing. I'm not saying it's like perfectly to scale, but this is 360 degrees. This is 270 degrees. Cosine of 1 over root 10. Square root of 10 is like what? Square root of 9 is 3, so square root of 10 must be a little bit more than 3. So I'm saying 1 over 3-ish. So a relatively short x leg. And then this hypotenuse should be square root of 3. Can I find out this other side right here? Can I find out the point that I'm sitting at? Well, I can use the Pythagorean theorem. 1 squared plus y squared is 3 squared. Root 3 squared, excuse me. So 1 plus y squared is 3. Y squared is 2. That means that y is plus or minus root 2. Now, because I'm in the fourth quadrant, I have negative y values. I'm going to name that point 1 and minus root 2. The length of this side as a triangle, I don't like to call lengths negative, so I'll call this root 2 long. But this point is 1 and minus root 2. This is the angle x. So your first reaction is, what does this have to do with 2x? This has nothing to do with 2x, and where in the world is 2x? Well, I'll draw that in a second if you like, but this is enough information to answer these questions. You know, by the identity, sine of 2x is equal to 2 sine x cos x. That's the double angle identity. So if I want to know the sine of 2x, all I have to do is read the sine and cosine from x. What's the sine of this x? Negative root 2 over root 3. That's the sine of x. Opposite over hypotenuse, y over r. What's the cosine of this x? Oh, excuse me. What am I doing? Suddenly I switched from root 10 to root 3. And I think I did that when I said what? That root 10 was about 3? I think I have to trash this. But that's okay. I'll just bring in another pad of paper. Okay, we're going to have to delay that. And let's redraw this angle, x. More generously, let's use more space. So let's pay attention to what I'm doing. Okay, sorry about that. Let's try again. So x is between 270 and 360. X is in the fourth quadrant. The angle's in the fourth quadrant. The cosine is 1 over root 10, which is a little, root 10 is a little more than 3. So this is a little bit less than 1/3. So I draw something, my proportion wasn't bad. It's got a ratio of 1 to root 10 for cosine. Then let's properly fill out this y. One squared plus y squared is root 10 squared. 1 plus y squared is 10. Y squared is 9. That's a little bit nicer. Y is plus or minus the square root of 3. plus or minus the square root of 9, which is 3. Since I'm going down here, this point is minus 3. I'm still going to stick to my idea of labeling triangles with positive sides, right? So I'm going to call this side length 3. Side length is 3, but I'm going in the negative direction. Okay, so now I know that the cosine of this angle is 1 over root 10. The sine of this angle is minus 3 over root 10. And the tangent of this angle, opposite over adjacent, y over x, is minus 3 over 1. This reference triangle is a ratio of 3 to 1, but this 3 right here is negative value. Okay, now let's go back to here. If I want to know the sine of 2x, all I have to do is multiply 2 times the sine of x times the cosine of x. And the sine of 2x is minus 3 over root 10. And the cosine of x is 1 over root 10. So when I multiply these together, I get negative 6 in the numerator. Root 10 times root 10 in the denominator is 10. That's minus 3/5. That's the sine of 2 times x. What's the formula for cosine of 2 times x? Well, remember I had 3 formulas. I can choose any one of these that makes it easier for me. They're all about the same amount of work. I'll take the first one, cos squared minus sine squared. Cosine squared x minus sine squared x. And we saw the cosine of this angle was 1 over root 10. Square that. We saw the sine of this angle was minus 3 over root 10. Square that. And what do I get? 1/10 minus 9/10, negative 8/10, or negative 4 over 5. Now, by the way, think about this. I just told you the sine and the cosine of that angle 2x. So I could draw 2x, right? We drew x between 270 and 360. If this is 1x, where would 2x land? If 1x is in the fourth quadrant and you doubled that, where would you land? Well, if you doubled 360, you would land at 720, which of course is another full circle around. If you doubled 270, you would land at 540, which is once around plus 180. So 2 times x must be either in the third or fourth quadrant. But I just figured out the sine of 2 times x was minus 4/5, and the cosine, the sine of 2 times x was minus 3/5, and the cosine of 2 times x was minus 4/5. So where is sine and cosine both negative? That's in the third quadrant. So when I double this angle that I drew, I must be landing in the third quadrant. And the y component must be 3, not radius 5. The x component 4, radius 5. I must be about at an angle like this. This point is back 4, down 3. This side length is 4 and this side length is 3. So visualize doing this red angle twice, coming up a full 2 times around. I'm going to land on this black angle here. And there is the point that talks about the vertex of this triangle right here, -4 and 3. There's the radius 5. And so the sine of this double angle, -3/5. And the cosine of this double angle, -4/5. Oh, sorry, I was writing off the screen. How does that help me with the problems here? Cotangent and tangent. Well, how do I figure out the tangent of 2 times x? I could say the tangent of 2 times x is just sine of 2x over cosine 2x. That's looking at this black triangle. Can you tell me what the tangent of that black triangle is? Opposite over adjacent, -3 y over x, -3 over -4, which is 3/4. I could do the cotangent because it's the reciprocal of tangent. Or I could say cotangent of 2x is the cosine of 2x over the sine of 2x, which would be 4/3. One more time for the tangent. Remember, I have a formula for tangent of 2x. 2 tan x divided by 1 minus tan squared x. I wanted the tangent of 2 times x if I replace the a with an x. So let's try that out and see if I get 3/4. 2 times the tangent of x over 1 minus tan squared x. Back to my drawing. The tangent of x is -3. This would be 2 times -3 divided by 1 minus -3 squared. I'm running a little bit down to the page into the bad drawing, but this is -6 over 1 minus 9, -8. And -6 over -8 is indeed 3/4. Now I ran too far into this bad drawing. And I don't want you to consider this bad drawing. So I'm going to shade that out. But this is the style that I have to do any one of these problems in. When someone asks you for the sine of 2x, cosine of 2x, the tangent of 2x, and they give you information about x, then you draw that angle x. And you fill the values of the trigonometric functions of x. Into the appropriate double angle formula. Let me give you another example. Let's say problem 13, 14, 15, and 16 in this section. If you know that the cosecant of t is the square root of 5, and t is in quadrant 2, can you find all of these values? Cosine 2t, sine 2t, secant 2t, and cosecant 2t. Okay, let's think about this for a second. I didn't give you a secant of 2t formula. I didn't give you a cosecant of 2t formula. You only have double angle identities for sine, cosine, and tangent. Well, what's the reciprocal of sine? Cosecant. So if you want the cosecant of 2a, you just got to calculate the sine of 2a and take the reciprocal. What's the reciprocal of cosine? Secant. If you want the secant of 2a, all you have to do is take the cosine of 2a and take the reciprocal. So you only need double angle identities for sine, cosine, and tangent. Then you can calculate cosecant, secant, and cotangent of any double angle you want by taking reciprocal. So let's draw a picture of this angle nicely. Okay, what is cosecant? Cosecant is the reciprocal of sine, right? So if the cosecant of t is root 5, that must mean the sine of t is 1 over root 5. Root 5 is about 2.2-ish, 2.25. So let's draw an angle in quadrant 2 that has a sine of 1 over root 5. It's not perfectly to scale, but let's call the hypotenuse root 5, and let's call this side 1. Let's figure out the x value, and then we'll totally know this angle x. Well, they called it t this time. Now from the Pythagorean theorem, what's this third side? What's this other leg right here? Say x squared plus 1 squared is root 5 squared. X squared plus 1 is 5. X squared is equal to 4. So that x is plus or minus the square root of 2. Plus or minus the square root of 4, which is 2, plus or minus 2. Now, I'm in the second quadrant, so the x is going to be negative value. And the reference triangle has legs of 1, 2, and hypotenuse root 5. I want to emphasize this. Sorry, I'm going to let someone else in the room here. I want to emphasize this, that when I draw the reference triangle, I like to draw the lengths of the sides as positive numbers, because no one can draw a triangle with a side length of -2. But I'm thinking about this x value as -2 because I'm in the second quadrant. I'm thinking of this y value as +1 because I'm going up in the second quadrant. So how do I find the cosine of 2t? I just take the cosine squared of t minus the sine squared of t. And now that I've drawn t, I can read the cosine and sine right away. What's the cosine of this angle T? Minus 2 over root 5. What's the sine of this angle T? 1 over root 5. Square both of those. Give me a 4/5. Right? Plus 1/5. That comes out to be a sweet number. This cosine of 2t, 4/5 plus 1/5 is 1. Sometimes when you come up with a number that's too nice like that, you get upset or nervous. Now, because I want to think, where is the cosine equal to 1? Cosine is equal to 1 in these quadrants. So something doesn't look exceptional to me here. So let's double check. Cosecant is root 5. It's root 5 over 1. Sine is 1 over root 5. That's 1 over root 5 there. This length is 2. 1 plus 4 square rooted root 5. Got it. The cosine of t that I've drawn there is minus 2 over root 5. When I square that, I get 4 over 5. The sine of t is 1 over root 5. When I square that, oh, good. Okay, so eventually I would have found my mistake. Austin found it quicker. I was concentrating on the numbers. 1 over root 5, perfect. But I was supposed to subtract them. Okay, I knew it wasn't that special. So I haven't drawn 2t yet. I have not drawn 2t. I've only drawn t. But the cosine of 2t is 3/5. Let's do the sine of 2t. Thank you, Austin. 2 times the sine of t times the cosine of t. 2 times the sine of t is 1 over root 5. Make sure you get your signs, plus and minus signs, correct when you fill this in. The cosine of t is minus 2 over root 5. Because sine is positive in the second quadrant, and cosine is negative in the second quadrant. Now, when I multiply these out, in the numerator, I'll get 2 times 1 times minus 2. In the denominator, I get 1 times root 5 times root 5 minus 4/5. So I know sine and cosine 2t, but I don't need formulas for secant and cosecant. What is secant? The reciprocal of cosine. So if I want the secant of 2t, I just take the reciprocal of the cosine of 2t. That's 5/3. And if I want the cosecant of 2t, I take the reciprocal of the sine of 2t, which would be negative 5 over 4. This is the thing that you want to take from this. If I give you enough information to draw t, in the past we said, well, now you know all 6 functions of t. But do you realize what the double angle identities say? If I give you enough information to draw t, now you can do all 6 functions of 2t. And in a moment, all 6 functions of 1/2 t. So if I give you enough information to draw an angle, not only can you find all the trigonometric functions of that angle, but you can find all the trigonometric functions of twice that angle, or in a moment, half that angle. Let's do one more problem from this section just to practice our identities. So on the second page of this section, he give you a bunch of identities to prove. And I don't want to pick out any particular one. How about 35? Because you've done some identity proving recently, and I'm going to have you do some more. So I want to give you some more illustrations. So prove this identity. The cotangent of theta is equal to the sine of 2 theta divided by 1 minus the cosine of 2 theta. So how do you prove this identity? Well, remember we had 4 basic ways to prove an identity. You always work from one side and you try to create the other side. Don't work on 2 sides at once. You take one side and try to turn it into the other side. And we gave you several rules of thumb. First, work from the more complicated side. Maybe in this problem, the more complicated side is the right side. Know all of your basic identities that you can substitute into. Sometimes when you use sines and cosines, when you resolve everything in terms of sines and cosines, it makes it simpler. And what was the 4th rule? Use all of your previous knowledge about algebra. Well, in this problem, I think the right-hand side is the more complicated side. So I'm going to work on the right-hand side and turn it into the left-hand side. And I'm going to use the double angle identities. So I'm going to replace sine 2 theta with 2 sine theta cos theta. If I've got 2 thetas on the right side and just single thetas on the left side, I'm going to have to get rid of these 2 thetas. What about the cosine of 2 theta? Now remember, I got a choice. I can write cosine of 2 theta is cos squared theta minus sine squared theta. Or I could write 1 minus 2 sine squared theta.
Can't see.
Oh, okay. Thank you very much. Let me bring this back here. My fault. I could write cosine 2 theta is cosine squared minus sine squared theta. Cosine 2 theta is 1 minus 2 sine squared theta. Or cosine of 2 theta is 2 times cosine squared theta minus 1. Any one of these 3 should fix this problem. And I can decide which one I want to use based on what would make this simpler. I've already replaced the top with 2 sine theta cos theta, right? What would make the bottom simpler? I see this 1 here, minus. I think about this form right here. If I put that in there, I would get rid of the 1. Now I got to use parentheses, right? Because I'm subtracting 1 minus 2 sine squared theta. I'm subtracting this whole thing. Cosine of 2 theta is 1 minus sine squared theta, 2 sine squared theta. So I had to subtract the whole thing. But once I do that, treat these 2 minus signs with respect. What do I have on the bottom? 1 minus 1 is nothing. And then minus 2 sine squared theta is plus 2 sine squared theta. What else did I have on the top? 2 sine theta, cosine theta. Now I get to cancel out one of the sine theta. There's a sine theta on the top. There's 2 factors of sine theta on the bottom. I get to cancel out the 2. And what's left? On the top, the only thing that's left is cosine theta after I cancel out the 2 and the sine theta. On the bottom, 2 is canceled, but there's 1 factor of sine theta left. So 4 steps here, and I turned the right side into the left side. Okay, that's a short one, but this shows you how you prove identities using the double angle formulas. If you have to prove an identity that's got double angles in it, what do you want to do? I want to get rid of those double angles as soon as I can, so I can make it match these single angles on the other side. Okay. Let's try the half angle formulas. Got too many pieces of paper on the desk. Okay. We went from the sum and difference identities to the double angle identities. Let me show you the half angle identities. This is not going to be as smooth and easy to remember, but let's focus on these 3 cosine formulas. How do you create the half angle identities? Let's focus on these 3 cosine of double angles, and in particular, the ones that I wrote in the red. So if I have the cosine of 2a is equal to 1 minus 2 sine squared a. You think about this as a double angle formula because you see a and 2a. Just change your perspective. It's a half angle formula too, because here's a angle 2a, and here's half that angle a. So let's change the 2a to an x. That doesn't look like it's particularly interesting. Cosine of x, 1 minus 2 sine squared. Now, if 2a is equal to x, that means a is equal to 1/2 x. See, that's what I said. This formula is you call it a double angle formula, but you could just as easily call it a half angle formula. Except it's not solved for the sine of the half angle. Right? Now let's solve this for sine of x over 2. Let's rearrange this until I isolate sine of x over 2. Well, I'll take the 2 sine squared x over 2 and I'll bring it to the left. I'll take the cosine of x and bring it to the right. I'll divide both sides by 2. And I still don't know the sine of x over 2. This is the sine squared. This is the square of the sine of x over 2. In order to find the sine of x over 2 legally, I have to take the square root of both sides. Now the problem is sines and cosines and the like. Well, when I take the square root of a number, square root of 4, if I say x squared is 4, then x is plus minus 2. So when I take the square root of both sides, I have to admit that the number that I produce could be positive or negative. So this is the first half angle identity. This is the sine of half of x. And you can compute it just by knowing the cosine of x, but you have to manually choose the right plus or minus sign in front of it. I'll demonstrate in a second. Let's do the other half angle formula. If cosine of 2 times a is 2 cosine squared a minus 1, that's a double angle formula. Sorry, I got too many papers on my desk today. That's a double angle formula. Change your perspective and think of it as a half angle formula by changing 2a to x. Then you'll write cosine of x is 2 times the cosine squared of x over 2, 1/2 x, minus 1. And now you can solve this for the cosine of x over 2. You'll add 1 to both sides. You'll divide, after you add 1, you'll divide both sides by 2. And then to finish the job, you have to take the square root of both sides. And when you do that, then you have to admit that the cosine of x over 2 could be plus or minus the square root of this number. So plus or minus 1 minus cos x 2. There's a little bit of symmetry between those two formulas, right? They're almost exactly the same, except this uses 1 minus cos x, and this uses 1 plus cos x. The pain for you is that you have to manually choose the plus and minus each time. So again, what this requires you to draw the angle that you're given so that you can tell whether you should be selecting the plus or minus here. Let me give you an example. Oh, and by the way, there is a tangent of x over 2 in a second. But this has 3 versions. The double angle formulas, the cosine had 3 versions. It's sine double angle, tan double angle, but 3 versions of cosine double angle. In the half angle identities, you have sine and cosine, and you have 3 versions of the tangent of a half angle. Before we write down those formulas, though, I'll come back to these formulas. Let's do an example. I'm picking one out in your book here. Let's say 5, 6, 7, 8, 9, 10. Look at this in the section 6.3. Excuse me, section 5.4. If I tell you that the sine of A is minus 3 over 5, and A is between 180 and 270 degrees, that's quadrant 3. Can you calculate the 6 half-angle values? Sine of A over 2, cosine of A over 2, tangent of A over 2. Then cosecant of A over 2, secant of A over 2, and cotangent of A over 2. Say it like I said it a few minutes ago. It used to be that if I described an angle to you, you could find all 6 values. Now, what we're learning today is if I describe an angle to you, you can find all 6 values of the double angle and all 6 values of the half angle. Let's try it out. So first, I better draw this angle. Over here in quadrant 3, between 270 degrees, between 180 degrees and 270 degrees. And the sine is minus 3/5. Sine is y over r. So they have a radius of 5 and a y value of minus 3. That means the side length right here is 3. After you see this triangle a couple times, you remember it. That means this side length is 4. But that x value is minus 4. So here's the point, minus 4, minus 3. And here's the angle A. So can I calculate the sine of A over 2? It's going to be plus or minus the square root of 1 minus the cosine of A divided by 2. So I can read the cosine of A from this picture. The cosine of A is minus 4/5. One minus negative 4/5 divided by 2, plus or minus. I'm not going to make a commitment yet. We'll have to do that in a second. But let's figure out this fraction first. 1 plus 4/5. 5/5 plus 4/5. What is 5/5 plus 4/5? 9/5 divided by 2, plus or minus the square root of 9/10. That's plus or minus 3 over root 10. Unless they tell me to rationalize the denominator, this is fine answer right here. Now let's think about whether this should be positive or negative. Let's think about where the angle A is. Angle A is between 180 and 270. So if A is between 180 and 270, Where is A over 2? Well, it's got to be between half of 180 and half of 270. If A is between 180 and 270, then half of A is between 90 and 135. That means it's somewhere in here. I'm sorry, somewhere in here between 90 degrees and 135 degrees. And what is the sine of an angle between 90 degrees and 135? It's quadrant 2. Sine is positive value in quadrant 2 because the y coordinate is positive. So that lets me choose this plus or minus. So that means the sine of A over 2 is going to be positive 3/5. Sorry. Positive 3 over root 10. I was mixing the two angles. Now, say, first of all, you're a little bit upset, like, I've got 6, and so far I've only done 1. Well, remember, all 6 of these are built out of sine and cosine. So the fact that I have sine of A over 2 is 3 over root 10, that immediately gives me the cosecant of A over 2, root 10 over 3. As soon as I figure out cosine, I'll have secant. With sine and cosine, I'll have tangent. And with tangent, I'll have cotangent. So all 6 values build on each other, right? Let's do the cosine of A over 2. It's the same formula, except it was 1 plus cosine A over 2. And we already said the cosine of A was minus 4/5. 1 plus minus 4/5 this time over 2. And this is 5/5 plus negative 4/5. 5/5 minus 4/5. That's 1/5 over 2. Don't forget the plus minus. So the cosine of A over 2 is plus or minus square root of 1/10, which is 1 over the square root of 10. Now I have to choose plus or minus, right? And again, I'll go back to my drawing. If A is between 180 and 270, then half of A is between 90 and 135. So I am in quadrant 2. A over 2 is in quadrant 2 for this A in quadrant 3. And in quadrant 2, the cosine is negative valued because the cosine is x over r and x is negative values. So this time, I need to choose the negative. Cosine of A over 2 is negative 1 over root 10. Okay, and I can fill in the rest of these values. Negative 1 over root 10. Secant would be negative root 10. I didn't plan my space very wisely. Sine over cosine, 3 over root 10 divided by minus 1 over root 10 would be minus 3. And cotangent, which is cosine over sine, minus 1 over root 3, or just the reciprocal of tangent, minus 1 over root 3. I can have either way. So now we're demonstrating. If you know the bare minimum about any angle, you know one of the trig values, And just where it lives, we've demonstrated you not only can find all 6 values for that angle, but you can find all 6 values for the double angle and all 6 values for the half angle. Notice, by the way, I did the tangent of the half angle without giving you a formula for the tangent of half angle. Because the tangent of the half angle was simply the sine of the half angle divided by the cosine of the half angle. But just for good measure, I'll show you how to write the tangent of a half angle. Now it's the sine of the half angle divided by the cosine of the half angle. So by the formulas we just worked out, it would be 1 minus cosine x over 2 and 1 plus cosine x over 2. Now if I invert and multiply here, I get to cancel a 2. So the tangent of the half angle is 1 minus cosine x divided by 1 plus cosine x, square rooted. But since this is always a positive number, again, I have to choose the plus or minus from a drawing. So this is 1 of the half angle for tangent. But I could give you 2 more useful forms by multiplying top and bottom by 1 minus cos x rooted, or 1 plus cos x rooted. What would happen if you took this formula and multiplied top and bottom by 1 minus cos x square root? Then in the bottom, you'd have 1 minus cos squared, a plus b, a minus b. 1 minus cos squared is sine squared, and the square root of sine squared just be a sine. And on the top, you have 1 minus cosine x, 1 minus cosine x. You have 1 minus cosine x quantity squared. Square root of that is 1 minus cosine x. So the beauty of this version is I get rid of the square roots. And when I get rid of the square roots, I don't have to choose the plus minus anymore. The plus or minus is automatically baked into the calculation. Now I could have multiplied top and bottom by 1 plus cosine x square rooted, and then I would have got this formula. So the half angle formulas, I have 3 versions of tangent. And in the double angle formulas, I only had 1 version of tangent, but I had 3 versions of cosine. Let me do one more identity. Let me do one more calculation with these formulas. Look at the identities in section 5.4. Look at number 27. Can you calculate cosine of 105 degrees? Using a half angle identity. the cosine of 105 degrees. 105 degrees is just what? Slightly past 90? In fact, it's 15 degrees past 90. So 15 degrees past 90, that's one of our famous triangles. That's a 15, 75, 90 triangle standing on its thin side. So I already know the cosine of that. But can I calculate the cosine using a half angle identity? Well, let's think about 105 as what? Cosine of 210 degrees divided by 2. Think about 105 as half of 210. Then use the half angle formula for cosine of 210 divided by 2. Plus or minus. Now you got to remember which one's plus and which one's minus, right? Sine of half angle formula, use 1 minus cos. Cosine of half angle formula, use 1 plus cos. 1 plus cosine of 210 divided by 2. And 210 degrees is 30 degrees past 180. This would be a famous triangle. This would be triangle with sides 1, root 3, and 2. Excuse me. The weather changed, and it's gotten colder, and you even saw snowflakes, right? Well, then, of course, I caught a cold. But thankfully, just a cold. So 210 degrees. What's the cosine of 210 degrees? Minus root 3 over 2. Oh, sorry. Thank you. The cosine of 210 degrees is minus root 3 over 2. Plus or minus 1 plus minus root 3 over 2 divided by 2 plus or minus. This is 2 over 2. 2 minus root 3 over 4. This is 2 over 2 minus root 3 over 2 is 2 minus root 3 over 2. Then you divide by another 2. So you get 2 minus root 3 over 4. And this is plus or minus 2 minus root 3 square rooted over 2. Now that's funny because I thought that cosine of 105 degrees, remember I know this triangle, right? And this side is like root 6 plus root 2 in height. This side is like root 6 minus root 2. And this side is like a 4. That's the ratio of the sides there, right? So the cosine of 105 degrees by that ratio should be minus root 6 minus root 2 over 4. And how's that coming out right here? Well, I have to be able to show that those two things are the same, right? So can you transform that into that by multiplying by an appropriate factor? I'm going to let you tell me. I'll let you think about this for a second. And you don't have to tell me right now because it'll take you a second to think about it. Why is this equal to the value I know here? And by the way, I need to choose the plus or minus also. So the plus or minus, since cosine Well, 105 degrees got to be negative. I'll choose the negative sign there. So these two numbers have got to be the same. How do I show that those two numbers are the same? I can make it easier to believe that those two numbers are the same by showing you the values on the calculator. But how do I know algebraically that they're the same? Let me type this in the calculator and show you that. 2 minus the square root of 3. Nope. I forgot the square root. Square root of 2 minus square root of 3. Got it? Divided by 2. And minus the square root of 6. Ugh. I'm not typing this in well. Minus the square root of 6 minus the square root of 2. Stop. Divided by 4. Those two numbers are exactly the same. And in a way, I prefer the one on the bottom because I haven't even thought what it means to have a square root inside of a square root. Well, it's just another calculation for the machine to perform, but if I had to do that by hand, I'm not sure what I would do. Square root of 6 minus the square root of 2 over 4, I could probably do by hand if I had enough time. But these two numbers are exactly the same. How would you show that? Now, as it is, we're at the top of the hour here, so I'm not going to keep you past this. Why don't you just think about this for fun, and maybe I'll bring it on Wednesday at the beginning. I mean, it seems that those are the same number. But how can I show you, apart from typing on my calculator, that those are the same number? Okay, go practice double angle formulas, half angle formulas, and then we'll use them some more on Wednesday. And I'll show you some other very cool formulas called the sum to product and the product to sum identities. Okay, dress warmly. Don't go outside and catch a cold, but it's supposed to warm up for the remainder of this week. But I'm going to go make myself a hot cup of tea and try to recover my voice. I'll also finish grading your exams, and I'll let you know as soon as I post them. Okay, you guys have a nice afternoon, and I'll talk to you later.